Hello everyone, welcome back to Decoder. Today we are going to jump into a really interesting puzzle. So it all starts with a question that you have asked your phone countless times. You are trying to go from point A to point B, and what is the most fastest and efficient way to get there? This is a classic problem. But what if the map itself is actually a little bit weird? What if instead of saving you time or money, the certain path paid you back instead to take it? Now that is a whole different ballgame. And so for a problem like that, we need a special kind of problem solver. This is a riddle we are going to be working with today. Imagine a network of cities that are all connected by flights. Some flights, as usual, have costs, which is a positive number, which means that you have to pay that certain cost to be on that plane. But there are some unbelievable promotional flights which offer you a negative cost, which means that they pay you to get onto that plane. Which is weird, right? Yeah, I think so too. Now, let's look at this diagram over here that shows us this data. We are trying to go from city A to city D, which is our final destination. And over here, you can see a few normal flights. A to B is 50 bucks and A to C is 100. But if you look all the way down at the bottom in this diagram, you can see that the flight from B to D costs a negative 40. This one weird flight changes everything and breaks most of the rules that we follow when doing such puzzles like this one. So when you have a case this tricky, you don't call in just anyone. You call in a specific individual. And that specific individual is the Bellman-Ford algorithm. Think of this algorithm as our methodical detective who was built specifically to deal with this kind of tricky and bizarre puzzles. Now, on paper, this algorithm's job sounds pretty straightforward. It finds the shortest path starting from one point, which is A here, to all the cities in the map. And its real genius is how it deals with those weird negative costs that are among the normal positive costs. How does our detective actually work? It doesn't rush things, it doesn't jump to conclusions, it's patient and it's not greedy. So it carries out this super careful investigation, interrogating every single connection, every flight path, over and over again until it is certain that it has found the truth. And this core process, this interrogation, has a specific name, edge relaxation. But you don't have to think too much about it. Just think of it like this. The detective keeps a trusty little notebook with him, which records the best known prices for each destination. And in each round of the interrogation, it goes to every flight path and asks, "Hey, can you help me find a cheaper way to get to where you're going? And also, can you improve on what I already know?" At the beginning, our detective knows next to nothing. But what he does know is that the cost to get to our starting point is 0, because that is where we are at right now. And for other destinations, we record it as infinity, which is just a fancy way of saying that we don't know yet. Now, we begin our investigation. Iteration 1, the first pass. Our detective goes through every single flight path and asks them one by one whether they can give us a better price or cost than, well, infinity. And here is what we have got from our first pass. You can see it over here. We found a way to get to city B for $50. Simple enough, right? Well, check out city C. The direct flight from city A to C is 100. But if we go from A to B, we can get it for $50 and then B to C for $20, which brings out the total cost for $70. Meaning, compared to the initial flight from A to C, we have now saved $30 since now the cost is $70. Now the detective's notebook gets updated. City D is still a mystery, still at infinity. But a good detective is nothing but thorough. Bellman-Ford algorithm knows now that with the info we just learned about the city C, there might be new paths, new cheaper paths that have been unlocked later down the line. So it does this process all over again. A second full pass interrogating every single flight just to be sure. And this is where the magic happens. The breakthrough moment. On this second pass, the algorithm re-examines the weird flight from B to D. The first time, we didn't have a good price for B, but now we know that we can get to B for $50. So the path to D suddenly becomes 50 minus 40. And now the shortest cost to get to our final destination from A to D has become $10. And just like that, the initial case has now been cracked. By being so patient and rechecking all of the evidence, our detective was not fooled by those negative costs. Instead, it used it correctly to figure out the true, cheapest path. So now, the detective's final report is clear. The absolute best way to get from point A to D is to go through B first, and then take that unbelievable promotional flight from B to D, which drops down our final cost from A to D to just a measly $10. You know, handling negative costs is not the Bellman-Ford algorithm's only trick. Its true superpower is what it does when the map or the puzzle is fundamentally broken. So, imagine, what if there was a path that lets you make infinite money? Imagine there's a series of flights that formed a loop, and every time you went through that loop, you were richer than when you started, which means that you had made more money while going through that loop of negative costs. Take a look at this. Let's say you could fly from B to D and then to some new city E, then right back to B, which is a loop now. You could add up the costs, negative 40 plus 10 and then negative 20. You realize that you just made $50 instead of paying $50. You could do that all day, right? And fly in a circle, making money forever. This is what is called a negative wage cycle. So, in a scenario like this, what is the shortest path? Well, if you think about it, the shortest path does not exist, because the cost could just get lower and lower, and the amount you will be earning instead of paying will get higher and higher until it reaches negative infinity. Because you can keep running that money-making loop forever. So here is the detective's secret weapon, its final ace of its sleeve. After it's done through all of its checking, and when it thinks it has found its best path, it goes through one more check just to be sure. And if any of those costs can still be improved after finding that true cheap cost, now the algorithm knows something is wrong. And then it basically yells, "Stop, the map is broken." Now we have a negative cycle. This might all seem like a really specific academic puzzle, but this ability to not just handle negative numbers but to detect these infinite loops is very valuable in the real world. So this is when you realize the Bellman-Ford algorithm's true strengths, especially when you put it against another famous pathfinding algorithm like Dijkstra's. See, Dijkstra's is fast, but the second you throw a negative cost in there, it just breaks. The Bellman-Ford algorithm may take time, it may even be a little slower, but it's the thorough specialist that you can count on when the case gets too complicated. So this is exactly why it matters this much. In computer networking, it is used to find stable routes for data and to spot problems. And in the world of high finance, it is literally used to find arbitrage opportunities, which are basically those infinite money loops, but with currency exchange. It really helps us check if complex systems have these kind of fatal logical flaws. So when you boil it all down, the Bellman-Ford algorithm does so much than just show us the cheapest path. It tests the very logic of the map itself. In the end, it doesn't just tell us how to get there, it tests if the map we are using is even making sense. And that kind of leaves us with a much bigger problem. If an algorithm can find the flaws in a map, what other broken maps in our world are just waiting for the right kind of algorithm to come find them? Well, that's a problem for another time. I'll see you in the next video.